Cover. Here is an opinion that will make some DBAs uncomfortable. Most PostgreSQL indexes should not exist. I have audited over 200 production PostgreSQL databases. The median table has 7 indexes. The median number of indexes that are actually scanned in a typical week is 3. The other 4 are ghosts, silently adding 14 to 40 milliseconds to every insert, burning cache pages that real queries need, creating vacuum work that slows down the queries you care about, and inflating your storage bill by 30 to 60%. And here is the part that really hurts: the team that created those indexes thought they were making the database faster. They were making it slower. Every single one of those unused indexes passed a code review where someone said this should help. Nobody asked the 3 questions that would have stopped it. Which exact query does this support? What does explain analyze prove? What write cost does this add? This session is not a feature tour of Create Index. It is a production operating method. We will teach you to design fewer, better indexes from measured evidence and to have the discipline to kill the ones that are not earning their keep. That discipline is worth more than memorizing every access method combined. Learning map. Stop me if this sounds familiar. A query is slow. Someone adds an index. The query gets faster. Everyone celebrates. 6 months later, writes are slow, vacuum is behind, and nobody knows which of the 43 indexes on the orders table actually matter. That is what happens when you treat indexing as a reaction instead of a discipline. The 4 layers you need, and most teams skip 3 of them, are storage, so you understand that indexes point back to heap tuples and every scan has a physical cost. Planner, so you understand why PostgreSQL ignores your perfect index. Method, so you stop defaulting to btree when GIN, BRIN, or a partial index would be 10 times better. And lifecycle, the layer almost nobody does, so you build safely, monitor usage, catch bloat, and retire indexes before they become write taxes. Here is the contrarian take: the most important index skill is not creating indexes. It is deleting them. A team that reviews and drops unused indexes quarterly will outperform a team that adds indexes reactively, every single time. Heap and CTID. Most developers think an index is a copy of the data that makes reads faster. That mental model is wrong, and it leads to bad design decisions. An index is a navigational structure. It stores keys and physical addresses, TIDs, that point back to heap tuples. When PostgreSQL does an index scan, it walks the index to find matching keys, then visits the heap to check MVCC visibility and fetch the columns the query needs. 2 trips, not 1. This is why 3 things that seem unrelated to indexing are actually critical. Vacuum health determines whether the visibility map is current, which determines whether index-only scans can skip the heap visit. Table bloat determines how many extra pages the heap visit touches. And include columns determine whether you can avoid the heap entirely. If you do not understand the heap-to-index relationship, you will keep creating indexes that look right in theory and underperform in production. First, btree index. Here is a number that should make you angry: 99,999,812. That is the number of rows PostgreSQL read and threw away to find one row on a table without an index. Every one of those rows was loaded from disk into shared buffers, compared against the predicate, and discarded. On a busy system, that is not just slow, it is stealing cache pages from every other query running at the same time. The fix takes 4 seconds to type: create index, a btree index by default. After that, the plan changes from seek scan to index scan. The query reads 4 pages instead of 812,345, and execution time drops from 34 seconds to 2 milliseconds. That is a 17,000x improvement from 1 line of DDL. But here is the part most tutorials leave out: a sequential scan is not always wrong. If your query returns 60% of the table, the index scan would do 60% of the random I/O, which is slower than one sequential pass. The proof is never the node name in the plan, it is the buffer count and execution time. Click through the lab to see the btree index scan versus the sequential scan. Planner requirements. This is the slide that explains why your perfect index gets ignored, and it happens to every team. For conditions must all be true for PostgreSQL to use your index, the operator must match the operator class, and index on email cannot help where lower email equals $1. The selectivity must justify random I/O. If your predicate returns half the table, a sequential scan wins. Statistics must be fresh. Stale analyze means the planner is making decisions based on data that no longer exists. And the cost model must favor the index random_page_cost, correlation, and effective_cache_size all affect the math. The not obvious insight: when someone says PostgreSQL is not using my index, the answer is almost never a PostgreSQL bug. It is one of these 4 conditions. Check them in order, and you will find the answer in under 5 minutes. The most common cause I see in production? Stale statistics after a large data load. Run analyze and the index magically starts working. Index scan versus bitmap scan. If your explain shows a bitmap scan instead of an index scan, most developers think something went wrong. It did not. The planner made a smart decision, and understanding why tells you something important about your data. Index scan fetches one heap tuple per index entry random I/O, one at a time. Great for 10 rows. Terrible for 50,000. Bitmap scan collects all matching TIDs first, sorts them by page number, then visits heap pages in physical order, converting random I/O into sequential I/O. For moderately selective predicates, this is dramatically faster. The tactical insight: if you see bitmap and combining 2 single-column indexes, that is PostgreSQL compensating for a missing composite index. It works, but a proper composite index on both columns would eliminate the bitmap overhead entirely. Every bitmapping in your top queries is a design opportunity hiding in plain sight. Index-only scans. Index-only scans are the fastest possible index access path, and they are lying to you about half the time. The name says index-only, but look at the heap fetches number. If it is high, PostgreSQL is visiting the heap anyway because the visibility map is not current. You designed a covering index, you expected 0 heap access, and vacuum is silently undermining your work. The Monday morning action: run this query on your busiest tables, select rel name, n_lib_tup, n_dead_tup, last_auto vacuum from pg_stat_user_tables order by n_dead_tup desk. If dead tuples are more than 5% of live tuples on a table where you depend on index-only scans, your auto vacuum is behind. Lower auto vacuum_scale_factor for that table. This single change can cut heap fetches to 0 and make your covering indexes actually work as designed. Composite index order. The most expensive indexing mistake is not a missing index. It is a composite index with columns in the wrong order. And it is everywhere. An index on created_at desk status tenant_id looks like it covers your query. It has all 3 columns. But if your query says where tenant_id equals 7 and status equals open order by created_at desk, that index is almost useless. PostgreSQL cannot seek to tenant 7 because created_at is the leading column. It has to scan the entire index. The rule is deceptively simple: equality columns first, then range/sort columns, then include for output. Reverse your index to tenant_id status created_at desk, and the query enters the tree at the exact position, reads rows in order, and stops after limit. The difference is not 2x, it is 100x to 1000x. Click through the lab. The wrong order index reads 84,000 buffers. The right order index reads 18. Same columns. Same table. Different order. That is the entire lesson. Leftmost prefix. Here is a consolidation trick that can eliminate half your indexes overnight: the leftmost prefix rule. An index on tenant_id status created_at serves 3 queries, where tenant underscore ID equals 7, where tenant underscore ID equals 7 and status equals open, and where tenant underscore ID equals 7 and status equals open and created underscore at January 1st, 2026. 1 index, 3 query patterns. If you also have a separate index on tenant underscore ID, it is redundant, drop it and save the right cost. The sort direction insight is equally valuable. If your query needs order by created underscore at desk, IDASC, a B-tree index on created underscore at ID cannot satisfy it because the directions are mixed. You need created underscore at desk, IDASC, explicitly. For top-end queries with limit, this is often the single highest value optimization in the entire system. It turns sort 10 million rows then take 20 into read 20 rows and stop. Covering indexes include. Include is the most misused keyword in PostgreSQL indexing. Here is when to use it and when it is actively harmful. Include adds columns to the leaf pages of the index so the query can return them without visiting the heap. Great for a lookup that returns ID, email, and status. Terrible when someone includes a 4 kilobytes John payload in every leaf page. Now the index is larger than the table, cache efficiency collapses, and every write maintains a massive structure. The rule: include only small, frequently returned columns on selective lookups. If the column is wider than 100 bytes, benchmark before committing. Now the contrary and take on unique indexes. They are the most underused index type in production. A partial unique index like create unique index 1 underscore active underscore subscription on subscriptions, user underscore ID, where status equals active enforces a business rule that no amount of application code can guarantee under concurrency. If you have business invariants, make the database own them. Your application will have bugs. Your index will not. Partial indexes. If you are not using partial indexes, you are probably maintaining indexes that are 10 times larger than they need to be. A partial index on where state equals ready for a job queue table indexes maybe 0.1% of the rows. A full index on state indexes all of them, including the 99.9% that are completed or failed and will never be queried again. The partial index is smaller, fits entirely in cache, costs almost nothing to maintain, and is faster to scan. The trap that bites everyone: prepared statements. If your application uses where state equals $1 with a generic plan, the planner cannot prove that $1 equals ready, so it ignores the partial index. Test with explain analyze execute, not just explain on an ad hoc query. This single gotcha has caused more production partial index failures than any other issue. The lab walks through all 3 stages: the bloated full index, the targeted partial index, and the prepared statement trap. Expression indexes. If your query says where lower email equals lower $1 and your index is on email, the index is invisible to the planner. This is the most common my index is not working bug I encounter, and the explanation is simple: the planner matches expressions, not column names. The fix: create index on users, lower email. Now the planner sees the same expression in the index and the query, and the match is exact. This pattern applies to every computed predicate date underscore trunc, day, created underscore at, payload dash customer underscore ID, coalesce, status, unknown. The bigger insight: text search is not one problem, it is 4. Equality and prefix like use B-tree. Substring search like I like %keyboard uses PG underscore TRGM with GIN. Full text linguistic search uses xvector with GIN. And pattern matching under certain collations needs text underscore pattern underscore ops. If you are using the wrong method for the pattern type, no amount of index tuning will help. The lab shows the expression mismatch, the fix, and the proof. Concurrent index builds. Create index without concurrently is the most dangerous DDL command you can run on a busy production table. It takes an exclusive lock that blocks every write for the entire build duration. On a 200 gigabytes table, that can be hours. I have seen this take down production systems. Create index concurrently takes longer, sometimes 2-3x longer, but it allows reads and writes to continue. The trade-off is always worth it in production. Always. The thing nobody tells you, if concurrently fails or is cancelled, it leaves an invalid index in your catalog. This ghost index consumes disk, gets maintained on writes, but cannot be used by the planner. You must check PG_index where not index valid after every concurrent build and drop the invalid entries. The lab shows the progress monitoring view. This is what you watch instead of guessing whether the build is stuck. Dropping indexes safely. Here is the most underrated performance optimization in PostgreSQL, dropping unused indexes. Every unused index on a write-heavy table adds latency to every insert, update, and delete. It consumes shared buffer pages. It creates vacuum work. It inflates backups. And nobody notices because the cost is distributed across thousands of writes per second. The lab shows the full workflow: find zero-scan indexes sorted by size, verify they do not back constraints, drop concurrently, and keep the create index statement for rollback. The Monday morning action: run the unused index query on your production database right now. I guarantee you will find at least 3 indexes consuming gigabytes that have never been scanned. B-tree operators. B-tree is the Swiss Army knife of PostgreSQL indexing. It supports more operators than any other access method, and here is a number that shows why. A B-tree on a billion-row table needs exactly 4 page reads to find any key. Root, internal, leaf. For random reads, roughly 0.1 milliseconds on SSD. But B-trees have a dirty secret: they bloat. Random inserts cause page splits. Deletes leave free space that is not immediately reclaimed. Updates create dead entries. Over months of production traffic, a B-tree can grow 30 to 50% larger than the actual data it indexes. That bloat means more pages in cache, more reads per lookup, and slower scans. The tactical action: run pkstateIndex on your largest B-tree indexes. If average_leaf_density is below 70% or empty_pages is more than 10% of leaf_pages, the index is bloated. Reindex index concurrently recovers the space. Schedule this quarterly on your top 10 indexes by size. Multi-column selectivity. This is the slide that explains why your perfectly designed composite index is being ignored, and the answer is not the index, it is the statistics. PostgreSQL estimates selectivity for each column independently and multiplies them. If tenant_id equals 42 matches 0.1% of rows and status equals open matches 15%, the planner estimates 0.015%, about 150 rows. But if tenant42 is almost all the open orders, the actual result is 120,000 rows. That is an 800x estimation error. The planner chose a nested loop expecting 150 rows. It got 120,000. The query explodes. The fix takes 30 seconds, create statistics orders_tenant_status, dependencies, MCV, distinct, on tenant_id, status from orders, analyze orders, rerun your query. Watch the estimate go from 150 to 118,000. Watch the planner switch from nested loop to hash join. Watch execution time drop 50x. If you have correlated columns and where clauses and you are not using extended statistics, your indexes are being underutilized right now. Hash indexes. Hot take: you probably do not need hash indexes. Ever. Hash indexes support one operation equality. No range. No ordering. No uniqueness. No distinct. No joins beyond hash join. B-tree does equality plus all of those. The only narrow advantage of hash is potentially smaller index size for very long text keys where the hash value is compact. In 15 years of PostgreSQL consulting, I have recommended hash indexes exactly twice. Both were edge cases with UUID columns wider than 128 bytes where the hash saved measurable cache space. For everything else, B-tree is the correct default. The lab shows what hash can and cannot do. The takeaway: if someone suggests a hash index, ask them to prove the size advantage with numbers. If they cannot, use B-tree. BRIN query pattern. BRIN indexes are the most underused index type in PostgreSQL, and if you have any table over 100 million rows with time series data, you should be using one right now. A BRIN index on a billion-row timestamp column is 2 megabytes. The B-tree equivalent is 22 gigabytes. The BRIN is 11,000 times smaller. It maintains itself for nearly free on writes. And for time range queries on physically ordered data, it performs within 2-5x of the B-tree while using 0.01% of the storage. The catch: BRIN is lossy. It stores min/max per block range, not per tuple. So the plan shows rows removed by index recheck, that is expected. And BRIN only works well when the physical page order matches the column value order. Check pg_stats.correlation. If it is close to 1.0 or -1.0, BRIN is a fit. If it is close to 0, BRIN is useless. The lab shows the B-tree versus BRIN comparison with real numbers. For append-only time series tables, this is the single highest ROI index change you can make. JSON. If you store JSON and you have not thought about your index strategy, you are either doing full table scans on every JSON query or maintaining a GIN index that is 5 times larger than it needs to be. JSON with John_path_ops is the right default for containment queries, where payload at customer_ID 42. It is 30 to 60% smaller than John_ops because it only supports at and does not index keys separately. If your workload is containment heavy, this is the right choice. But here is the non-obvious insight: if every query filters the same JSON path payload-customer_ID, a B-tree expression index is 10-20x smaller than any GIN index and supports equality, range, and ordering. The GIN index is a general-purpose hammer. The expression index is a scalpel. The third insight is GIN write performance. Fast update buffers changes in appending list. Under heavy writes, this list grows and slows reads until vacuum merges it. If your GIN index table has variable query latency, check GIN_pending_list_limit and auto vacuum frequency. Just concept. Exclusion constraints are the most powerful indexing feature that almost nobody uses, and they solve a problem that application code literally cannot solve safely. The problem: prevent overlapping hotel bookings for the same room. Application code checks for overlap, finds none, inserts. But between the check and the insert, another transaction does the same thing. Both succeed. You now have a double booking. No amount of application logic fixes this race condition. The database fix: altered table bookings add constraint no_room_overlap exclude using gist room_ID with equals period with and. Done. The database enforces no overlap atomically under any concurrency. This is not a performance feature, it is a correctness feature backed by a gist index. SPGIST handles partition search, init ranges, text prefixes, quad tree spatial data. Use it when the operator class exists for your data type. Bloom index extension. Bloom indexes solve one specific problem that nothing else handles well: ad hoc equality queries on many column combinations. Think of a fact table with 20-dimension columns where users filter on arbitrary subsets. Without Bloom, you would need hundreds of composite B-tree indexes or accept full table scans. With Bloom, one index covers all equality combinations at the cost of false positives and heap rechecks. Measure Bloom against targeted B-trees before committing. In most systems, 3 to 5 well-designed B-tree indexes beat one Bloom index. But in true ad hoc analytics workloads, Bloom can be the right tool. Trigram indexes. The search bar on your application probably does I like %user input %. Without a trigram index, that is a full table scan on every keystroke. PG_TRGM breaks text into 3 character fragments and indexes them with GIN. After that, I like %keyboard % uses a bitmap index scan instead of reading the entire table. The improvement is typically 100-1000x for selective search terms. The warning: trigram indexes can be large, sometimes larger than the table itself for text-heavy columns. And they are expensive to maintain on write-heavy tables. Use them for real search paths that users actually type into, not for every text column in your schema. The lab shows the progression: B-tree fails on leading wildcard, trigram GIN succeeds, and the size warning reminds you to benchmark before deploying. Full text search. If you are using like or trigram search for natural language queries, you are solving the wrong problem with the wrong tool. Full text search normalizes words, removes stop words, applies stemming, and searches lexemes, actual language understanding, not pattern matching. The implementation pattern: add a generated vector column, index it with GIN, and query with add and squery. The generated column is automatically maintained on writes. The GIN index provides sub-millisecond lexeme lookup. This is one of the most underused PostgreSQL features. Teams run Elasticsearch clusters for search that PostgreSQL handles natively with zero additional infrastructure. For 80% of application search use cases, vector plus GIN is sufficient, simpler to operate, and transactionally consistent with your data. Range types. Range types with GIST are the correct tool for any "does this overlap" query. Scheduling systems, reservation platforms, time-windowed access control, all of these need overlap detection, and all of them benefit from exclusion constraints that make the database own the invariant. For partition tables, the key insight is that indexes are per partition. A create index on a partition table creates matching indexes on each child partition. Unique constraints must include the partition key. And your queries must include the partition key and where to enable pruning, otherwise PostgreSQL scans every partition's index. Foreign keys. PostgreSQL does not automatically index foreign key columns. This is the most common missing index pattern in production, and it causes two different problems. First, parent delete and update operations must check the child table for references. Without a child side index, this check is a sequential scan of the entire child table, holding locks the entire time. On a million-row child table, this can block all writes for seconds. Second, joins from parent to child use nested loops by default for small outer sets. Each loop iteration needs to look up child rows by the foreign key. Without an index, each iteration scans the full child table. The Monday morning action: query PG_constraint and PG_index to find every foreign key without a matching index. Create indexes on the ones attached to tables with more than 100k rows. This is one of the highest ROI index audits you can do. Indexes for aggregation. Deep offset pagination is a performance anti-pattern, and most applications are doing it right now. Offset 10,000 limit 50 means PostgreSQL reads and discards 10,000 rows before returning 50. Page 200 of your results is 200 times more expensive than page 1. The fix is seek pagination. Instead of offset, use where, published_at, ID, $last_ts, $last_id, order by published_at desk, ID desk limit 50. With a matching index, every page costs exactly the same. The index seeks to the last seen position and reads 50 rows. For aggregation, the best index matches where first to reduce input, then provides group by order to avoid a sort. Include can cover the aggregated column to avoid heap fetches. But be honest, if the query aggregates most of the table, no index helps. Use a parallel sequential scan and stop fighting the planner. Prepared statements. Generic plans are the most common cause of the same query is fast for one user and slow for another, and most teams do not even know generic plans exist. After 5 executions, PostgreSQL may cache a plan based on average selectivity instead of the actual parameter value. If tenant1 has 12 rows and tenant9 has 9 million rows, the same plan serves both badly. The symptom is intermittent slow queries that are impossible to reproduce in testing. The diagnostic: set plan_cache_mode equals force_custom_plan and run the slow query again. If it is dramatically faster, the generic plan was the problem. The second hidden trap: operator class mismatch. An index using text underscore pattern underscore ops cannot help a query using default text equality under certain collations. When an index exists but the plan ignores it, check the operator class before anything else. Include versus composite key. Here is a question that will immediately tell me how well someone understands PostgreSQL indexing. What is the difference between a key column and an include column? Key columns participate in search, ordering, and uniqueness. The B tree organizes pages by key values. Include columns are just payload stored at the leaf level, they cannot be searched, sorted, or deduplicated by the tree structure. If you put a column in include when it should be in the key, the index exists but PostgreSQL cannot use it for that predicate. If you put a column in the key when it should be in include, the tree is unnecessarily larger and updates to that column require index maintenance. The hot update insight: every index on a table reduces the chance of heap-only tuple updates. A hot update avoids creating new index entries when no indexed column changed. If you have 15 indexes on a table, almost no update qualifies for hot. That is real, measurable write amplification. Fewer indexes means more hot updates means faster writes. Index bloat. Index bloat is the silent performance killer that nobody monitors until queries start timing out. Over months of writes, B-tree indexes accumulate dead entries, split pages, and fragmented free space. A 10 GB index can balloon to 15 GB while containing the same data. Those extra 5 GB compete for shared buffers, increase every scan's I/O, and slow down every query that touches that index. The monitoring query: select asterisk from state index, your underscore index, and look at average underscore leaf underscore density. Below 70% means significant bloat. The fix: reindex index concurrently. This builds a clean replacement alongside the bloated original, swaps them atomically, and drops the old one. The deeper fix: understand why the bloat happened. If the table gets heavy updates on indexed columns, consider fill factor to leave room for in-page updates. If auto vacuum is not keeping up, tune auto vacuum underscore scale underscore factor lower for that table. Treating the symptom, reindex, without treating the cause, vacuum health, means the bloat will return. Monitoring index usage. The most important index monitoring query you will ever run is: select index rel name, idx underscore scan, pg underscore size underscore pretty, pg underscore relation underscore size, index relid, from pg underscore stat underscore user underscore indexes order by idx underscore scan asc, pg underscore relation underscore size, index relid, desk. This shows you every index sorted by least scanned and largest first. The top results are your most expensive waste, large indexes that nobody queries but that every write maintains. The lab walks through interpretation, combine scan count with size to prioritize. A zero-scan 200 GB index is an emergency. A zero-scan 2 MB index is a minor cleanup. Check constraints before dropping. Verify across the full workload cycle, not just one quiet hour. And always keep the create index statement ready for rollback. Do this once a quarter. I have never not once audited a production database and found zero waste. There is always something to drop. Duplicate indexes. Duplicate indexes are free money on the ground. An index on tenant underscore ID is completely covered by an index on tenant underscore ID status created underscore at. The single column index adds write cost, consumes storage, and competes for cache, while providing exactly zero additional query capability. The detection is simple: query pg underscore index and look for indexes on the same table where one index's key columns are a prefix of another's. The action is even simpler: drop the shorter one, verify no queries regressed over 48 hours, and move on. The harder version: finding indexes that are almost duplicates, same columns but different order, or overlapping partial predicates. These require plan analysis. But exact prefix duplicates are safe wins every time. Hypo-PG what-if indexes. Hypo-PG is the fastest way to answer "would this index help?" without paying the build cost. It registers a hypothetical index in the planner's catalog, lets you run explain to see the plan change, then removes it. This is perfect for narrowing design choices. Test 5 different column orders, test partial versus full, test B-tree versus GIN all in seconds, without building anything. But remember, HypoPG shows the planner's estimate, not actual runtime. After you choose the winner, build it for real and validate with Explain Analyze. Explain Index Checklist. Stop calling it a win just because the plan says index scan. I have seen index scans that read 84,000 pages and removed 500,000 rows by filter. That is a terrible index being used terribly. The real proof, actual rows match the estimate. Shared reads dropped significantly. Heap fetches are near zero. Sort nodes disappeared. P95 latency improved under production load, not just in your test session. The lab shows both, a successful index scan that is actually worse than a seek scan, and a properly designed index-only scan that reads 18 pages with zero heap fetches. The difference is not the node name, it is the work removed. This explain checklist should be applied to every index change without exception. Anti-pattern index every column. 3 anti-patterns that I find in almost every production database I audit. 1. Indexing every column. A team had 47 indexes on their orders table. 11 were used. The other 36 added 14 milliseconds to every insert, that is 140 seconds of wasted CPU per second at their write rate. The right number of indexes is the smallest set that supports correctness and high-value query paths. 2. Wrong column order. An index on, created_at, status, tenant_id, for a query that filters where tenant_id equals 7 and status equals open. The planner cannot seek to tenant 7 because it is the third column. Reverse it. Same columns, 100x faster. 3. Function mismatch. Index on email, query on lower email. The planner sees a different expression. Use an expression index or switch to citext. Every index should have a named owner, a named query it supports, and a review date. If nobody can explain why an index exists, it should not exist. Case study slow API. Real case, a tenant-scoped API endpoint went from 3 milliseconds to 9 seconds after the orders table grew past 50 million rows. The team's first instinct was to add an index on, created_at desk. It did not help. The problem, the query filters by tenant_id and status first, then sorts by created_at and id. An index starting with created_at cannot seek to the right tenant. The fix, create index posts_feed_api_idx on posts, tenant_id, status, created_at desk, id desk, include, title, author_id, summary. The result, 50 rows, 18 buffer reads, sub-millisecond execution. Every rule applied, equality columns lead, sort direction matches, tiebreaker makes pagination deterministic, and include avoids heap fetches for the display columns. This is not theory, this is the pattern that handles millions of API calls per day. Case study time series. 2 patterns that save the most money at scale. Time series, stop using B-tree on billion-row timestamp columns. A BRIN index is 2 megabytes instead of 22 gigabytes. It is 11,000x smaller, nearly free to maintain, and handles time range queries efficiently on physically ordered data. Check pg_stats.correlation first. If it is above 0.95, BRIN is the right tool. JSON search, stop using broad GIN indexes when you always filter the same path. A B-tree expression index on, payload-customer_id, is 10-20x smaller than GIN with job_path_ups. Use GIN only when you genuinely need to search arbitrary keys. Use B-tree expression when the path is stable and the operation is equality. Production checklist. Every index request should answer 4 questions before anyone types create index. 1. Which exact query, with which parameter values, at which frequency? The API is slow is not a request, it is a symptom. 2. What does explain analyze with buffers show? Which node is expensive? Is it a scan problem, a sort problem, a join problem, or a statistics problem? 3. Which method fits? B-tree for equality, range, and ordering. Brin for huge ordered tables. Gin for John, arrays, and text search. Gist for ranges and exclusion. The operator determines the method, not the column type. 4. Who owns the lifecycle? Who monitors usage? Who reindexes when bloat appears? Who drops it when the query changes? An unowned index is a future write tax. B-tree deduplication. 3 B-tree advanced features that most teams ignore. Deduplication compresses repeated keys using posting lists. If your status column has 3 values in 50 million rows, deduplication stores each key once with pointers to all matching tuples. This makes B-tree indexes on low cardinality columns much smaller than you would expect. But a plain index on a low cardinality column is still usually wrong. A partial index on the rare value where state equals ready is the right tool. It indexes only the hot slice, stays in cache, and costs almost nothing to maintain. Fill factor leaves room on B-tree pages for future inserts, reducing page splits and bloat. Default is 90%. For update-heavy tables with random key patterns, try 70 to 80% and measure whether bloat growth rate decreases. The index starts larger but may stay healthier over time. Cluster and physical correlation. Physical correlation is the hidden variable that makes the same index fast on one table and slow on another. When heap pages are physically ordered by the index key correlation close to 1.0, an index scan reads contiguous pages. When they are randomly scattered, correlation near 0, every index entry requires a random heap page read. The planner uses this number to decide between index scan and bitmap scan. Cluster rewrites the table in index order. It is a heavy operation exclusive lock, full rewrite, but it can improve index scan performance dramatically on tables where correlation has degraded. PG_repack does the same with less locking. For deep debugging, StateIndex shows B-tree levels, leaf density, empty pages, and deleted pages. These numbers tell you whether reindex will help. Index size is not just disk, it is a memory and I/O budget that affects every query touching that table. Build progress monitoring. Long index builds are stressful. PG_stat_progress_create_index removes the guessing. The progress view shows whether the build is scanning, sorting, building, or waiting. Waiting is the phase that causes panic, the build is waiting for old transactions to finish. Do not kill it. Check PG_stat_activity for long-running transactions and address those instead. The invalid index trap: if you cancel or kill a concurrent index build, it leaves an invalid entry in PG_index. This ghost index gets maintained on writes but cannot be used by the planner. Check for invalid indexes after every interrupted build, select index_relid reg class from PG_index where not indexvalid. For build speed, set maintenance_work_mem equals 2 GB before a large build. This controls the memory available for sorting during index creation. But set it per session, not globally. Concurrent maintenance operations multiply the demand. Exclusion constraints. Exclusion constraints are correctness infrastructure, not performance features. They solve problems that application code cannot solve under concurrency. Use GIST-backed exclusion constraints for any business rule involving no 2x can overlap and y. The toast warning is about include abuse. If you include large text, John, or bytea columns in an index, every leaf page carries that payload. A covering index that includes a 4 kilobytes document body on a table with 10 million rows adds 40 gigabytes to the index. That is 40 gigabytes competing for cache, maintained on every write, and included in every backup. Cover only what materially reduces heap access, small columns on selective lookups, not entire documents. Final decision tree. When someone says add an index, start here. Not with create index. Step 1. Which exact query? Get the SQL, the parameter values, the frequency, and the latency target. The dashboard is slow is not actionable. Step 2. What does explain analyze show? Run it with buffers. Find the expensive node. Is it a scan problem? A sort? A join? Bad estimates? Or something outside indexing entirely, locks, connection pool, application and +1? Step 3. Design the index from the evidence. Method, columns, order, predicate, include, operator class. Use hypo-PG to test before building. Step 4. Build with concurrently. Monitor with pg_stat_progress_create_index. Verify the plan changed as expected. Step 5. Operate it. Monitor IDX_scan. Watch for bloat. Schedule reindex when evidence says so. And if the query changes, have the discipline to drop the index instead of adding a new one on top. This is the entire session in 5 steps. Everything else is detail. Thank you. The best index is not the cleverest definition. It is the smallest structure that makes an important workload fast without making writes unhealthy. Here is what I want you to do this week. Run the unused index query on your production database. Find the 3 largest zero-scan indexes. Verify they do not back constraints. Drop them concurrently. Watch your write latency improve. That is the beginning of index discipline. Build fewer indexes. Build them from evidence. Prove them with explain analyze. Monitor them with pg_stat_user_indexes. Reindex when bloat appears. Drop them when they stop earning their keep. 3 questions before every index decision. Which query does this support? What does the plan prove? What write cost does this add? Thank you for joining Dr. Ibrar Ahmed. Now go delete some indexes.